So these are from the ACS study guide, page 52, number 1. So it gives you choices A, B, C, and D that says what reagents could accomplish the synthesis of this compound. So I'll write those choices down, and then you have to evaluate which pair of nucleophile electrophile is suitable to make that specific compound. So probably when you're given a compound, you want to think about what the name is, because sometimes you can just look at the carbon count of the answers and eliminate choices that way. So here are the 4 possibilities to make that compound. What do you think the name of that compound is? Something hexine. 2-hexine. So you're looking at the choices of an electrophile and nucleophile pair that have to make 2-hexine. So a strategy you can use to begin with is just count all the carbons in both of those pairs to make sure they add up to 6. Then you can look at is the alkyne in the right place. And then this is going to be an SN2 reaction where you have a nucleophile and an electrophile. So if you're looking at the possibilities, what do you think the best choice to make that compound is? What? It is A.
A and D both have 6 carbons.
So
You really drop them in 6 because they both have either more than 6 or less than 6.
right. So this. Count. So if you sort of map these 3 right here, 1, 2, 3, this is only going to be good to 5. This has the same 1, 2, 3, usually 4, 5, 6, 7, so that's too many. This is like no reaction. So at this point, you should be able to see that this is not. Mixing these 2 together is not going to do anything. It's definitely not going to give you that. You have basically an alkyne, which is neutral, and an alkane, which is neutral, and there's no leaving group on either of them. Remember we said, so the Br is a good leaving group because it can support the negative charge. H minus is not a good leaving group. And then that gets back to the pKa. So you have a nucleophile. Acetylide anion attacks that carbon, that then leaves. You get sodium bromide as a byproduct, and then that's your final product. So let me ask you a follow-up question. So in 2-hexyne, how many unique type of carbons do you have? You have 6. So each carbon is unique. How many unique type of protons do you have? So the 2 carbons of the alkyne do not bear any hydrogens, so that's why you have less than 6 unique sets of H. So now my next question. An alkyne is a carbon-carbon triple bond. Do you remember where you see triple bonds in the IR?
25 or 2000 to 25.
Yeah, so within that region. I'm going to just narrow it down a smidge and call it 2,000 to say 2,400. What other triple bond functional group can you think of? So the nitrile. So really, those are the only 2 that you would ever see in that region. So if you see a peak in that region, it's either got to be a nitrile or an alkyne. Then you can look at the molecular formula and distinguish. If there's no nitrogens, it has to be an alkyne. Does that raise any questions you might want answered?
Do you mind going over HNMR and 13C3R? I'm
Just-
very bad at that, I'm sorry.
Just like in general?
I know the relevance of like CNMR where it's just counting the unique carbons. And
Right.
It's not as relevant as H1, but it's more of just making structures with NMR, or IR, NMR, and then HNMR.
Okay.
Because we were doing it in lab and I was just having trouble with them.
Let me think of a way to sort of phrase this. Okay, so this will be another one from the study guide. We actually did this one a while ago in class, but I'll sort of rephrase it to you in a different way. So page 149, number 13. So they give you a spectrum and it says which structure is consistent with this spectrum. So I'm not going to draw the spectrum because I want to like take you through the thought process first. So you'll sort of see it on the exam tomorrow as well. But first let's go through and just count the unique number of H sets for all of these. So include the ones that are bonded to the OH as well. So count that as a unique set in each one. So for A, how many unique sets do you have? So yeah, that's just 2. What about for B? Three? So this is what, probably the reason you said 3 is because you have 3 Cs2s in a row, and you're counting those as 1. But that's not true, because you're basically looking at, if you like start here, that H, the relationship of these to that is different. So then these all have to be different. So this ends up being 1, 2, 3, 4, 5. Then C you have. So yeah, these are going to be 4. And so this probably what might trip you up if you don't realize the way this is drawn. So like this is sort of like a right angle. So that might look different from that. But it's actually symmetrical. So that's 1, 2, 3, 4. And then finally D is 5 as well. So to a first approximation, what this is useful for, if you were given the spectrum, you could count 1, 2, 3, 4. So if there was 4, then you would say immediately it's this, without even having to look at the splitting or anything. So that's the benefit of determining uniqueness. If the spectrum showed 5, you could eliminate A and C then. But you'd have to choose between B and D. So if we dig a little bit deeper, maybe we'll just go through all of them so you can sort of see like the next level of thinking that you need to do rather than just look at B and D. But since B and D are both 5, you need another way of distinguishing them. I'm just going to redraw these so it's a little more palatable to the eyeballs. So the structure of A is this. So there's 2 unique sets. How would you describe the multiplicity of each set? Like, what is the peak shape and what is the integration? So you're going to have 2 singlets. Does everyone see that? So the methyl groups are all equivalent. There's no beta hydrogens, so it's going to be a singlet that integrates to 9. So just write, and then this will be a singlet that integrates to 1. So the next one gets a smidge more complicated. I think I'm putting too many there. So let's start at this end. What is that peak gonna look like, and how many protons will it integrate to?
Triplet, triplet,
So it's going to be triplet 3H. So you're just counting the number of H's bonded to it. So it only has 2 neighbors, so 2 plus 1 is 3, and that's your triplet. So moving in the chain, this next one down here, what should that be? So yeah, we got, I don't even know what you call that, if that's the right name for that or not. That's 2H. The reason that it's sort of, if you go on to take chemistry 404, that it can't be that is because the couplings become degenerate, and then the number of, you can't have that many lines, like 6 lines, because they collapse in on one another and you get something simpler. But that's why I don't know the name. Call it a sextet. I don't know if that's right or not. So 2H, then if you go into the next one, this one up here, another methylene group, so 2 H's in what multiplicity? So yeah, quintet. Pentet, whatever. Again, really, if you do this for a living, it's when you get to the higher multiplicities, they're called doublet of doublet. So it'd be like a doublet of doublet of doublets rather than like a quintet or something. And then finally, the last one, this CH2.
Is that a triplet or a quartet? Do you count like the hydrogen, like oxygen?
So normally you would not, but in this case, if we do, we say that 2 plus 1 is 3. We would call it a quartet. So we'll just do that for simplicity's sake. So we go out here, we have a quartet that integrates to 2H. Then this would be a triplet that integrates to 1H. And so what you're going to find when we go through the rest of these, like I said, even though these are like degenerate, this is not going to have those type of signals. So that's how you would tell from there. Let's just do this one. So this, the CH3s will be what? A doublet that integrates to 6. So I'm going to change the color here. And then this one in the center, that 1H would be, so yeah, we'll just call it a multiplet. Because you have 6 plus 2, so that's 8, plus 1, that's 9. And you would never have like a non-net or whatever. So it's just, so we'll call it a multiplet that integrates to 1H. Then we have a CH2, so that's 2 H's, and then that would be what? So 1, 2 plus 1, that's 3, so a triplet. That would be a triplet. So you can see as you do this sort of analysis, it's going to look different. Then maybe for this one we can just go through and we'll just write them above here. This should be what? So triplet should be quintet, 5, quintet, 5-tet. This will be or sextet, hextet. That would be doublet. So we said triplet. So pentet. 5. So wait, we had 6, 7. No, wait. Can't fucking that one. So 3, multiplet. So, yeah, those things, I guess I wouldn't worry too much about. H. So you can see this is what's going to differentiate those, is doing the assignment of those peaks. Let me, does that raise any other questions? I don't think I did this one last night, so maybe I did do that one. Try to pick one I didn't do. So this is page 56, number 27. So you're given 4 bromides. And it says, which bromide will most rapidly undergo solvolysis in aqueous ethanol? So what does that mean? It's basically an SN1 reaction. Yes. So lysis means cleavage, solve means solvent, so solvolysis. What's the classification of all of those bromides? So they're all secondary. So right there, they're all going to form secondary carbocations, so you can't differentiate just on that fact alone. There's other things at play here. Do you remember the sp3 hybridized carbon next to an alkene is called what? What? Allylic. So vinylic is the thing right on the bond itself. So this is an allylic carbon. So the secondary allylics are going to beat out these two. So you can eliminate B and C from contention. And we'll show you why. But between A and D, which one do you think is going to be faster and why? D. Why do you say that? You're like, you want to shoot as fast as you can. How?
Which means it'd be an option for some growing way, but that's what felt longer.
So you know, I would say basically things can be boiled down to like ultimately electronegativity. But there's two things, induction or resonance. So the argument here is going to be resonance. So we'll draw it out, but this oxygen has lone pairs, right? And so let's draw the bromine ionizing. We'll show that carbocation, and then we'll show why that oxygen being there helps. So remember, in an SN1 reaction, ionization is a slow step. But if all of these things were in a flask competing, A would be the fastest one to undergo the reaction. So I'll draw it stepwise so that you see. So that's the bromine leaving. That's the ionization event. So this has a resonance form. And now it has another resonance form where the oxygen can donate in. Draw that in red as well. And so the more resonance forms you have for something, the more stabilized it is. So D can form 3 resonance hybrids. Once this ionizes, you get a carbocation here. It can be stabilized this way or that way. So this one, the presence of that oxygen facilitates more resonance forms. C and D, or sorry, C and B, once that carbocation ionizes, it's just stuck right there. So how would this look maybe on an energy curve? So I'm going to just say they're all sort of hanging out sort of at some close energy. When you ionize something, you're always going up in energy because the carbocation is unstable. So A is going up like the least amount. Then we'll say D followed by B, and then C is the highest. So that's what we mean by things that are stabilized at lower energy relative to anything else. And so the reason the ionization event is slow is because wherever you're starting from, you're going up in energy. So however you want to think about it, if you were a little atom-sized person on this hill, like pushing a marble up or something, it's going to be easiest to go here, pushing that marble all the way up there. So things that are unstable are really high in energy. So do you remember what this point is called? The highest point on all of them? So yeah, that's a gimme 4 points right there. And then this is what? That's the intermediate. So that it's basically, those are the words that classify like the time frame those things exist. So let me take a problem out of the textbook. So this is as written. Rank the 3 carbocations shown in terms of increasing stability. So if we want them ranked in increasing stability, what would the order be? Say it again. So how did you arrive at that? What was your reasoning? So we'll just put under the ranking here, this is primary, secondary, and tertiary. So carbocation A is tertiary, so it cannot rearrange. So B and C can, so why don't we draw those so we understand what's meant by a rearrangement. So it can be sort of confusing with carbocations maybe, if you're not used to thinking about that implicit hydrogen. So that's what B looks like. So I put that hydrogen in so you see it. So that's a secondary carbocation. And so what I'm going to do, I'm going to call the carbocation carbon A. For a rearrangement to occur, it can only occur in a certain fashion. It can't just be willy-nilly. So what you have to do is look to the carbons next door. There are 2 of them. I'm going to call this the beta carbon and the beta prime carbon. Then you're examining those either for hydrogens or a methyl group that can shift over. What you're trying to do is make a more stable carbocation. So if you look at, the reason I use prime is that these are different. This has 3, this has 1. So a way to think about this is the beta carbon bearing the least amount of hydrogens is one that will shift a hydride over, because that will then form a more stable carbocation. This has more hydrogens. If something shifts over, you'll get what type of carbocation? Primary. So the beta carbon that has the least amount of hydrogens will do the shift. So let me draw that in. Maybe I'll use blue. So here's that hydrogen, and I'm calling this a hydride. So hydride is H minus, because this proton is taking these 2 electrons and it's moving over. So you're forming, maybe I'll leave the H there, just move the bond over, and then the carbocation comes over here. So this shifts over. I just totally effed that up. That should not be there. So it's shifting over here now. So we go from secondary, now it's tertiary. So what's happening is that the electrons in that bond move over the reason that this can happen, again, if we think about it in terms of a energy coordinate, how many people, did anyone go to that physics lecture last night? Just one? So this is basically these energy surfaces. Like, she didn't show specifically an energy surface, but that's what's happening when DNA coils back on itself. It is finding a well amongst like millions of possibilities. It's almost scary to think like why humans exist. I mean, it's pretty wild. So maybe let's draw. Let me think about how I want to draw this. So here's the well that we're starting in. I don't want to call that time necessarily. So that secondary carbocation is at some energy. When it rearranges, it's got to go through a little bit of a transition state to do that. So it's going down in energy. The reason it won't go the other way is because it would have to go up in energy. So that's a way to visualize what those rankings mean when we talk about the general order of carbocation stability. Let me take another problem from the book here. So this is what type of carbocation? It's secondary. So again, whenever you have a primary or secondary, you have to consider, can it rearrange to something more stable? So primary can go to secondary or tertiary. Tertiary can go to, or secondary can go to tertiary. So because this is secondary, you have to look at the beta carbons. This has 3 hydrogens. This doesn't have hydrogens. But the methyl group can shift. So that can happen. So we have secondary. Again, I'll draw this in blue. So now you have tertiary, but it's also further stabilized because the carbon next to a benzene ring, so benzene ring, the carbon next door is called benzylic. So you need to know allylic and benzylic, what those terms mean. Questions? Yes.
Is your one with inversion of stereochemistry?
Yeah. Maybe we'll just leave it at that for now. So when you're diagnosing this, I think that's probably a good word to use. It's predict the product, but to do that, you have to understand something about the mechanism. So the first thing you want to do is, if you can, name it. If you don't want to spend time doing that, write down some functional groups, and then classify those functional groups. So you have an alkyl bromide in there, and then you have an ether. So what classification of bromide is that? So it's a secondary. What's the stereochemistry of that carbon bearing the bromine? What? So R, everyone buys R. So we have R stereochemistry. So let me be clear. That's useful, but this does not tell you necessarily about inversion in an SN2 mechanism. It's like this wedge and dash convention that tells you about if inversion occurred. You have to figure this out no matter what. Don't assume that when an inversion occurs, like R is going to go to S, and S goes to R, because that's not true. That's not always true. So you have a secondary halide. So those are the ones that are in between. Does it go SN2 or SN1? So the way you diagnose which way it's going to go is based on these. EMF is polar aprotic, so that should clue you into SN2. Sodium cyanide, you have metal cation, strong anion, so that's a good nucleophile. Good nucleophile, polar aprotic solvent, so it's SN2. That's telling you that complete inversion occurs. So if we look at the mechanism, so how should I draw the bond to the cyano group? What? We have wedges versus dashes. We're gonna get into a royal rumble here. How many people say wedge? 1. Dash. I think the dashes have it. So the cyano group's going to be this, and then the hydrogen's going to get the wedge. So see that the hydrogen, I didn't draw it here, but when this attacks, it's now coming forward, and so this has to be in back. So that's what we mean by inversion. What of that stereogenic carbon, what's the R or S nomenclature for it now? I think it's R. So this is your lowest priority group, right? So when you go out, you hit carbon, carbon, carbon. So those are all equal. These are all hydrogens. This has 3 nitrogens. So if we look up there, nitrogen 7. This has an oxygen. So I think this wins. So 1, 2, 3. So you're going S, but that's towards you, you should reverse it to R. I could be wrong. I don't like ambiguous cases like that. The reason I say it's ambiguous is because the oxygen's 8, then the hydrogens are 1 and 1. So nitrogen's 7, so this is a triple bond. You would view it as 7, 7, 7. I think what you go with is if one has a higher number, automatically wins. But I'm not 100% certain on that. I'm not an expert on anything.
So on the test, is it going to be easier to figure out?
It should be. So if it is that, again, that's just the demonstration of why you can't assume R becomes S and S becomes R. Because there are certain nucleophiles you can use where the order definitely changes. So we'll hedge our bets. I'll put it into a program and see what the program spits out. I'll let you know. Yeah.
Nucleophilicity, like, if we're giving a reaction and we're asked to determine the best conditions for it to happen, how would we go about that?
So let's use this nucleophile here. So you have sodium cyanide versus hydrogen cyanide. So nucleophilicity, if you think about the broader term like Lewis basicity, a Lewis base is something that supplies a pair of electrons. This is an ionic bond, sodium cyanide. The cyanide owns that pair of electrons. In hydrogen cyanide, it's shared. It's a covalent bond. So this is a better nucleophile compared to that. So typically, something that has like a discrete anion is better than something that is neutral.
Let's say we're comparing ethanol and methanol and is this? What is this?
That's an acid. Ethanoic acid. So, let me just put up these other pairs and we'll sort of compare them all. So there was so that's the same argument. You have sodium acetate versus acetic acid. This is going to be a better nucleophile than that. You can have the alcohol versions as well. So sodium ethoxide versus ethanol. So the top ones are going to be better nucleophiles. So what if you were comparing across different things? That's the question. So if you had these two, the alcohol is going to be the better nucleophile. I think this will be a better nucleophile because, again, the nucleophile is supplying the lone pair of electrons. In here, it's just on that oxygen. In here, it's delocalized. So it's spread out. And so between like this and that, when you have the sodium salts, this is going to be a better nucleophile than that. So let me draw it out so you can see that. So usually resonance stabilization is a good thing. But in terms of nucleophilicity, where you're supplying an electron pair, it's stuck on that oxygen. In here, it's delocalized amongst two of them. So it's not as ready to bond as when it's the alcohol version. So let's do a SN1 reaction. So what are some things you know about SN1? What happens in terms of the mechanism? So it's forming a carbocation, and you need to evaluate the stability of the carbocation that forms. So let's do two things here. What sort of substrate are we starting with? What's the classification of the halide? So it's secondary. What's the full IUPAC name of that compound, including stereochemistry?
2,4,3
And what's the stereochemistry? Which, where's it? So 2R, what about 3? I think it's R as well. So 2R, 3R. So in an SN1 reaction, you have a polar protic solvent. So notice there's no other like nucleophile present. That's another indication. It's unimolecular substitution. You have a secondary leaving group. The thing you cannot assume is that where this leaving group is, that the substitution is just going to take place there, because you have to look for a rearrangement of the carbocation. So we said that's secondary. So we have to draw what it is and evaluate, can it rearrange? So this is the slow step, the ionization event. So notice what happens. I'm going to draw that hydrogen in. So a secondary chloride forms a secondary carbocation. So you look to the left, look to the right, the different beta carbons. We said that the beta carbon bearing the least amount of hydrogens is the one that could potentially rearrange, right? When this leaves, that stereochemistry is destroyed. It no longer exists, right? Because this is sp2 hybridized. So this has 3, if a rearrangement took place this way, what would happen? You'd get a primary carbocation, right? So if a rearrangement from this carbon took place, the hydride shift would give you primary. So if you look over here, there's a hydrogen here. If that moved over, what would you get?
Tertiary.
Tertiary. So secondary can go to tertiary. So when this is ionized, that stereochemistry is destroyed. When this rearrangement happens, what happens to that stereochemistry?
It gets restored. Tertiary.
So yeah, it goes away as well, because that carbon is now sp2 hybridized. So let me put this one in red. So now the solvent can attack from the top or the bottom. So the solvent coming here or there equally. So I'm just going to put a couple arrows. You get a proton transfer. And so because it does that, you're destroying all the stereochemistry that was present at the start. So what you're ending up with is essentially the following molecule. I'm missing something here, right? Something looks not right. Why is that not erasing? That shouldn't be H, right? I don't know why that's not erasing. I think I put an H there. That should just be a CH3. Then what the fuck's happening here? All right, there's the eraser. So this should be CH3. Is that? I think that's right. Maybe. Changing these colors. So CH3, ethyl, ethyl. So, long story short, that would be the final product. It doesn't have a stereogenic carbon anyway, because the ethyl groups are the same. But basically, when an SN1 reaction happens and a carbocation is formed, the stereochemistry goes away. And you no longer get an inversion because of this carbocation. The nucleophile can attack from either face, and so we call it racemization. So I would say on the exam, take your time. You know, I spend a couple hours dreaming up these questions, so I don't know, like trying to, I don't know, get you or get you to fall into a trap or something. Don't fall for my stupid tricks. If you're given a name, just convert that structure or convert that name into a structure so you understand like what those choices are. So if your choices are A, B, C, and D and their names, unless you can visualize all four of those things in your mind at once, I would just draw them all out, then sort of evaluate from there. It's going to resemble the first 3 exams. There's going to be a pharmaceutical drug, a couple questions about it. Then it transitions into how it relates to the substitution stuff. Then you're given some spectral data that you have to figure out. Just pay attention to the spectral data. There's little clues in there that help you figure out what the unknown is. Then that goes into a couple questions about the actual mechanisms and predicting the products of things. But I think that answer choices are sufficiently differentiated that you can, if you know a little bit about this stuff, you can get rid of the BS choices and end up with the right thing. But my biggest advice is just like breathe and take your time. Again, people are gonna be getting up within 10 or 15 minutes. Don't let that freak you out. That's not your performance. Just let them be. Form your own little place of zen. Don't let some other person induce stress in you. So, any last questions before we wrap up?
How much of the exam is practice? Like, would you say, is it more important than substitution than radical?
There's probably 5 distinct questions dealing with that, where you have to, at least 3 of them, you have to refer to the table, do some sort of math. You don't need a calculator, it's pretty straightforward.
Is there going to be any elimination on this test? Since
No.
we've gone over substitution.
This is just substitution. We're gonna finish off the semester with elimination. So, it sort of tracks with how you classify these things, but then the nature of these reagents will tell you if it's a substitution or an elimination. So there you just have to know what something does, if it acts as a nucleophile or a base. But we'll get into that on Friday.
So for this exam, like, just really just know, like, the different, like, how rearrange carbocation, like, strong nucleophiles and stuff, like, know the characteristics of the different reactions.
Yeah, so given any like substrate with a leaving group, be able to classify the leaving group, then look at the solvent involved, look if there's a strong nucleophile, that'll tell you if it's SN2 versus SN1. And then given any alkane, to do radical substitution, be able to classify the different types of CH bonds.
Would there be any, energy diagram?
Yes. They're, I don't know, if you know what a transition state is and know what an intermediate is, it's pretty straightforward. Any further questions? If not, I mean, you can feel free to email me. I'll try to answer within a reasonable time frame before the exam.